Hello all and welcome to the next session of the course Pre-MBA Statistics. So again, just in the last session we sort of rushed through the idea of estimation. So we started, if you remember in the last session we started with sampling distributions, which was kind of okay, that we talked about T distribution, and even before we talked about chi-square distributions, and we sort of put forward that how do you derive these distributions from a normal distribution, or so be it a standard normal distribution or general normal distribution, but these are called as sampling distributions. And why? Because these are distributions of certain sampling quantities. So be it x bar, be it s square, etc. Okay. And then towards the later half of the last session we talked about estimation more from a point estimation point of view. So what do you mean by point estimation? Point estimation is nothing but, let's say, I'll try to summarize it very quickly. If you start with a parameter theta, okay, and generally we assume that parameter theta is unknown. So if something is unknown, we have to estimate that using the data set you have, all right. And then we sort of put forward some estimators of the parameter theta. And notation wise, the estimator notation is nothing but theta hat. So we say that, let's say, if you bring a practical data set and if you want to somehow, let's say, estimate theta, which is, let's say, mean, okay. So if you assume that theta is nothing but the population mean, then how do you sort of put forward an estimator for the population mean? And then we saw in the last session that all these are sort of usual estimators to begin with. So be it x bar, or be it, let's say, median of x, okay, or we talked about trimmed mean, or I can sort of put forward x1 also as an estimator. So all these are valid estimators of the population mean, which is mu. Now the more importantly, the question is that how do you compare them? So which one of the estimators is slightly better, or how do you sort of compare all these estimators and a lot many more, okay. And then the idea was mean squared error, or MSE, okay. And then formula of MSE is what? Formula of MSE is expected value of theta hat minus theta whole square. So you take the estimator, you subtract the parameter, and this sort of gives you nothing but the deviation of the estimator and the actual parameter theta, and then it's a squared quantity. So whichever estimator is giving the least value of MSE, that estimator is the best one, okay. So up till now we have talked more about point estimation. Point estimation means what? You're proposing a single point as an estimator of theta, which is theta hat. Okay, so now we'll delve deeper into what you call as a confidence interval. So rather than proposing a single point, something like theta hat as an estimator, can I sort of propose an interval? So theta hat minus, let's say, A and theta hat plus B. So you have an interval as an estimator of theta. So I am proposing this entire interval as an estimator of the unknown parameter theta. And this underlying idea is called as confidence interval. So you might have heard about, let's say, people proposing a 95% confidence interval, 90% confidence interval, etc. Okay. So we'll kind of see the differentiating point between a confidence interval and a point estimator to begin with. And then of course we'll see some examples as to how do you construct some confidence intervals, and so on and so forth. Okay. Alright, so again, just to begin with, so what is the idea called as a confidence interval to begin with? So a point estimate of a parameter is a single number. So as discussed in the last slide or just in the beginning of today's session, that a point estimator is nothing but a single number, let's say theta hat, and we're sort of proposing theta hat to be a valid estimator of theta. So a point estimate of a parameter is a single number which is unlikely to be the true value of the parameter. So let's say if you're proposing a single value as an estimator of theta, then this theta hat is very rarely going to be very close to theta, or this theta hat is very rarely going to be the exact value that theta has, or theta takes, okay. So which is unlikely to be the true value of the parameter. Hence many a times what we do is we are interested in getting a confidence interval. So in short, we call a confidence interval as CI. So whenever you see CI in this session or even later, a CI stands for a confidence interval. So a CI is calculated by fixing a confidence level first. So all these are ingredients. So we'll talk about very shortly as to how do you sort of come up with the confidence interval, which is CI. So any CI is calculated by first fixing a confidence level. So what do you mean by confidence level? So initially, let's say you fix a small value called as alpha. So the small value called as alpha, And again, alpha is a small number. So let's say 1%, 5%, at the max 10%. Okay. So let's say you fix alpha to be, let's say 5%. So 5% means 0.05. Okay. Then the confidence level is nothing but 1 minus alpha. So if alpha is my 5%, then confidence level, which is 1 minus alpha, happens to be 95%. Okay. So then, the moment you fix the confidence level, we can talk about a 95% CI. Okay. So any CI or any confidence interval has to begin with a confidence level to begin with. So let's say 1%, 5%, 10% is the alpha number. And subsequently, if you do 1 minus that number, so 1 minus 1% or 1 minus 5%, 1 minus 10%, that becomes my confidence level. Okay. So hence you must have seen people saying that you're sort of interested in constructing a 95% CI or 90% CI, etc. Okay. Alright, so we'll begin this entire idea about a confidence interval with a small example. So this is an insects example. So example revolves around or focuses on insects. Suppose an investigator is interested in the average length mu of a certain species of insects when they mature. Okay, so let's say if you have a collection or if you have a set of data which tells you the length or the average length mu. So each and every xi in the data set is length of a certain species of insects when they mature. And the investigator is sort of interested in finding or having a rough idea about the average length. So the entire problem revolves around sort of estimating the mean here. Okay, so estimating the average length mu of a certain species of insects. Then a random sample of 30 insects was collected. Okay, so n becomes 30 here. So random sample of 30 insects was collected. The lengths of the insects are as given below. So these are all the individual lengths of each and every insect which is being collected. Okay. So immediately I can find out certain summary variables. So if you feed in this data in, let's say, some Excel or some software, I can sort of calculate these numbers immediately. So x bar is 30.15. So the sample mean of this entire data is nothing but 30.15. Okay. So a point estimator of mu, we can take very well to be 30.15. So my mu hat becomes a point estimator which is 30.15. But now can we do better? So better in what sense? So can we have some sort of an interval around mu rather than a point estimator? Okay. So again, you can pause the video, you can sort of digest what you're trying to achieve here, what is the data set here. So again, just to summarize, you have an insects data, each and every value here in the table below gives you the length of a certain species of insects when they mature. And now you have to sort of find out a rough idea about the average length of those species. Okay. So as a point estimator, I can propose x bar to be a valid point estimator. However, since we are almost certain that mu is not equal to mu hat, okay, so 30.15 need not be exactly equal to the unknown mu. So can we instead give a possible interval which can cover mu with certain confidence? And hence the entire problem boils down to finding a suitable CI with a certain confidence level. Alright, so again within this confidence interval, sort of the broad spectrum, we have different ways or different kinds of intervals. So we'll start the discussion with confidence intervals for mean of a normal population. So again, couple of important properties here or assumptions here, that we sort of assuming that the collected data set or the set of random variables follows a normal distribution to begin with. And again, the focus parameter here is to find out the interval for the mean of the normal population. So the entire focus is to find out a CI for mu here. Okay. Alright, so how does the problem start, or how do you begin with sort of stating the problem? So let x1, x2, x3 up to xn be a suitable sample from a normal population having mean mu and variance sigma square. Then as discussed in the last session, from the sampling distribution section, x bar also follows a normal distribution with the same mean mu but variance sigma square by n. This is the first assumption, or rather a first property we require. Okay. So if you start with a sample coming from a normal population having mean mu and variance sigma square, then my sample mean is also normal with mean mu and variance sigma square by n. Okay. Now how do you standardize this? So for standardization, you subtract the mean divided by standard deviation. Okay. Now since my x bar minus mu divided by sigma by root n is a standard normal variable, so this quantity happens to be z. So we can sort of very well make use of this property, or make use of this important property or important idea. So this is a standard normal variable. So what we do is we put this entire standard normal variable in the middle, and then we take suitable quantities on the left hand side and right hand side. So 1.96, or rather 1 minus 1.96 on the left hand side, 1.96 on the right hand side, and again we will talk very briefly as to why exactly this number 1.96. But it so turns out that why 1.96, because this probability happens to be exactly 95% which we want. Okay. So again remember, what are we trying to achieve here? We are trying to construct a 95% CI, isn't it? So we are trying to construct a 95% CI for mu. So firstly you should understand what you mean by 95% CI. So 95% CI means once you propose a lower bound and an upper bound, okay. So once you propose an interval or a CI, then you have a 95% chance that the unknown parameter mu falls in that interval. Or rather, a more correct way to put forward is that if you sort of simulate 100 such samples, okay, if you sort of come up with 100 such simulated samples, then roughly 95 of them should contain, that interval should contain the actual mu. This is the significance of 95% CI. Okay. So again, when you are sort of proposing an interval for mu means what? You have to propose a lower bound and an upper bound. Okay. So something like a comma b. So if you are able to tell me both a and b, this is a valid interval for me, or valid CI for me. So this is an example of a CI. Okay. And then what we want is that probability that a should be less than, mu should be less than b should be roughly equal to 95%. Okay. This is the actual meaning of constructing a 95% CI. Similarly, if you are constructing a 90% CI, this number would change to 90 here. So depending on the confidence level of the CI, this equation should hold true. Okay. So hence we will see that why are we sort of bringing this quantity first and not mu. So are we sort of interested in having this in the middle? No, we are sort of interested in having mu in the middle. Okay. But this is a standard normal quantity, so we can make use of standard normal tables or its properties, and then it so turns out that 1.96 is a perfect value. On the left hand side you have minus 1.96 and you have 1.96 positive on the right hand side, such that probability that minus 1.96 is less than a standard normal variable, which is z, and less than 1.96 on the right hand side happens to be 95%. Okay. So this is the starting point for creating that interval. Okay. So we put forward a standard normal in the middle, then we sort of formulate or find out two numbers, minus 1.96 and 1.96, such that this entire probability happens to be 95%. And now what? So now can you try to sort of answer the question that how can you sort of have only mu in the middle? So now the answer is simple. So you sort of adjust this entire equation such that you only have mu in the middle. But otherwise, the entire probability and this 0.95 on the right hand side stay the same. Okay. So the first step would be, let's say, cross multiply by sigma by root n, then sort of subtract x bar, then take a negative sign throughout, flip the signs, etc. Okay. So this is exactly what we will do now. Or let's say this is the final step where you only see mu in the middle and nothing else. Okay. So x bar minus 1.96 into sigma by root n is less than mu, is less than x bar plus 1.96 into sigma by root n, and again the probability stays the same, which is 95%, and now the thing is done here. Okay. Thus the summary point is what? Thus if x1, x2, x3 up to xn be a sample from a normal population having mean mu and variance sigma square, then the probability that the above random interval contains mu, again just to summarize, then the probability that the above random interval contains mu is 95%. So what is my final interval here? So my final interval is lower bound comma upper bound. So lower bound in this case is this part. So x bar minus 1.96 into sigma by root n, and the upper bound is x bar plus 1.96 into sigma by root n. So this entire lower bound comma upper bound is a 95% confidence interval for mu. Okay. So again, I totally understand that you have to sort of again go over this example one more time. How do you, what is the starting point here? Then from that starting point, how do you adjust the equations? Okay. For example, cross multiply by sigma by root n, then subtract x bar, take negative signs, change the signs, right? And so on and so forth. But finally, you have to ensure that you only have the parameter or the underlying parameter in question in the middle. So that then you can simply pick up the lower endpoint, the lower bound, and the upper endpoint or the upper bound as a Ci. Okay. Now, a small point here. So, let us say if I change this 0.95 to let us say 0.9 or 0.99. So, automatically this 1.96 number would change, isn't it? Because now the probability which I want is no longer 95%, but it is let us say 90%. Then accordingly from a normal table or the properties of a standard normal distribution, you can pinpoint to a different number apart from 1.96 there. Okay. So, this is exactly how you are sort of fixing this 1.96 number here. Okay. So, this 1.96 to begin with is ensuring that this probability happens to be 95%. Alright, so now the idea is to put forward a general confidence interval, but then for that we require one very important idea called as critical value. So, what do you mean by critical value? So, let us say you fix some number C between 0 and 1. Okay. So, C is a constant between 0 and 1. So, for any C between 0 to 1, Z subscript C. So, ZC denotes the Z critical value such that for any standard normal variable Z, this equation should hold true. Okay. So, probability of that standard normal variable exceeding the critical value should be C. Okay. So, probability that the standard normal variable exceeds the critical value ZC happens to be C. Okay. So, again this is a visual depiction of that. So, for example, what do you mean by Z alpha by 2 then in that case? So, in that case Z alpha by 2 would be a point such that the area on the right of that number is alpha by 2. Okay. So, again we are sort of utilizing this equation here, okay, isn't it? So, let us say this is a Z curve, this is Z density curve, standard normal density curve, and this would be this point here on the x axis is a critical value, and which critical value? Z alpha by 2. So, alpha by 2 is there in the denominator, which means that the area on the right of that point should be nothing but the subscript, which is alpha by 2. Okay. So, this is just a definition and you should kind of sort of memorize this definition, that what do you mean by any critical value. So, if you start with a constant C in 0 to 1, then what do you mean by that? Okay. This is nothing but the meaning of a critical value there. Alright. So, once you know the definition of a critical value, we can sort of very quickly formulate some standard CIs coming from a normal population. So, again a CI for a normal population mean. So, this would be the first one. Now, this is a very general notation that people use to denote any CI. 100 into 1 minus alpha percent CI. So, what do you mean by this? So, if you fix alpha to be let us say 0.05, so how much is this number? So, 1 minus alpha is 0.95. So, 100 into that number would be 95% CI. Okay. This is the meaning of 100 into 1 minus alpha percent. Similarly, if I fix alpha to be let us say 0.01 only, this number would be 99%. Okay. Alright. So, 100 into 1 minus alpha percent CI for the mean mu of a normal population when the value of sigma is known. So, this is an important assumption here. We will talk about two different scenarios. The first case sigma is known, second case sigma is unknown. Okay. So, if sigma is known, we can very well make use of sigma in the interval formula. Now, what exactly is the interval formula? So, again from the last example we saw, if you try to compare that last interval we found out in the last slide for the insects example, it looks quite similar to this formula here. Okay. So, from here you may pause the video and try to tell me that what was this Z alpha by 2 number from the last insects example. So, the critical value from the last insects example was in fact 1.96. Okay. So, if you plug in 1.96 here and minus 1.96 here, you will get the exact same interval we saw in the insects example. Okay. Anyways, but then this is the interval for a normal population mean. So, if you start with a normal distribution or set of random variables having a normal distribution, then a 100 into 1 minus alpha percent Ci for the unknown parameter mean of a normal population happens to be exactly that. Or this is many people use this standard notation also. So, rather than writing down a lower bound comma upper bound structure, I can write down x bar plus and minus Z alpha by 2 into sigma by root n. So, more generally a general formula for the Ci is nothing but a point estimate. So, in this case what is a point estimate? In this case a point estimate of mu is nothing but x bar, isn't it? So, my mu hat is nothing but x bar, which we also saw in the beginning of today's session, in the last session as well. So, if you are proposing a point estimator for an average or population mean is nothing but x bar. Okay. So from this equation I can see that a general formula to write down any Ci is you start with a point estimate plus and minus a suitable critical value, in this case is Z critical value, and then times the standard deviation or standard error of the point estimate, which is sigma by root n. Okay. So in this case the standard deviation of x bar happens to be what? Standard deviation of x bar happens to be sigma by under root n there. Okay. Now the more important or the most important point here is whenever you have a normal population and sigma is known, okay, whenever you start with a normal population and sigma is known, the underlying distribution of the critical value is nothing but normal. Okay. So hence we are using a Z critical value here. Okay. So all these properties are important. So we are creating a Ci for a normal population mean, assuming that the variance or the standard deviation is known. So under this entire scenario, we can sort of assume that the underlying critical value or the distribution happens to be normal here. Alright, so again a small example in the earlier insects example, suppose we also know that the lengths of all the mature individuals of the species follows a normal distribution. On top of that, you can sort of assume that the standard deviation of all the lengths is 3. So this is a classic example of what we studied in the last slide there. Then a 95% Ci for mu is nothing but, so if you remember the formula, you start with the point estimate of mu. So you simply find out x bar, my x bar happens to be 30.15. So you start with x bar, then plus and minus a suitable critical value. So in this case again, how do you arrive at this 0.025 number? So in this case my alpha is 5%, 1 minus alpha is 95%. So I want a 95% Ci. So how much is alpha by 2? So alpha by 2 is nothing but 0.025. Which is exactly what you see here. Okay. So again, if you remember the idea of, or rather the formula from the last slide, it was Z alpha by 2, isn't it? So the critical value there that you see in the formula is Z alpha by 2. So alpha by 2 here is 0.025. Okay. And then times sigma by root n. So now how much is sigma? Sigma is 3 and under root n. So n is 30. Okay. Now this quantity is how much? Can you tell me? So this quantity is nothing but 1.96. Okay. So again, like I said, you have to sort of remember 2-3 quantities here. So whenever you are creating a 95% Ci, the appropriate critical value happens to be 1.96. Okay. If you are creating a 99% Ci or 90% Ci, then things are, or that number is slightly different there. Anyways, but then ultimately if you sort of find out the lower bound and the upper bound, they come out to be 29.076 comma 31.224. So what do you now actually mean by this interval? I mean, finding or solving a problem is okay, but how do you interpret the interval? So in the interpretation of these two numbers is that if you sort of collect or go on collecting insects, let's say over 100 days, okay, so each day you collect 30 species or look at lengths of 30 insects, okay, and you sort of simulate or you replicate the experiment over 100 days. So how many samples would you have? You'll have 100 such samples, okay. Then 95 of those samples, there will be a situation where the value of mu would lie in this interval here. So between 29.07 to 31.22. Make sense? Similarly, now if I change this 95% Ci to 99% Ci, then again the idea is exactly same, but the only difference is instead of Z 0.025, you will have Z 0.005 now, okay. And then this number happens to be somewhere around 2.68. So instead of 1.96, you have 2.68, but otherwise things remain constant. So now the final interval happens to be 28.739 comma 31.561 there, okay. So this is exactly how you can solve a Z interval. Now what exactly is a trade-off? So we call this a trade-off. So the width of any 100 into 1 minus alpha percent Ci is given by this. So what exactly is the width? Width is nothing but upper bound minus lower bound is the width of any interval, okay. So a couple of very interesting properties here. So as the sample size, or rather at the same sample size n, so first property is at the same sample size n, if you increase the confidence level, so let's say initially you have 95%, but then you increase that to 99%, then what would happen to the width of the Ci? Okay, so the higher the confidence level, the wider is the Ci. And why is that? Because let's say at 95%, if you remember this number Z alpha by 2 was 1.96, but a short while back I told you at 99% the same number is 2.68. So naturally the width would increase. Okay. So if you sort of change 1.96 to 2.68, my entire width would also increase. So first property is that for a fixed n, if you go on increasing the confidence level, which is 1 minus alpha from let's say 95% to 98% to 99%, the wider my Ci becomes. Okay. However, a wider Ci has a lower precision. So if my width is more, then my overall interval is not very accurate, right, because you will have a wider interval. At the same time, the second important property is that if the sample size increases, okay, then what would happen? So again, from the same formula I can see easily that if I go on increasing my n here, and where exactly is n in the formula? N is in the denominator. So if I increase n which is there in the denominator, then the width of the Ci decreases. Thus, accuracy or precision increases. Okay. So couple of very important properties. These are all of these are interview questions. So let's say down the line when you will go into the MBA and then you will go into some interviews, all these are possible interview questions that one can ask, that how would the width of any Ci change depending on let's say the sample size or the confidence level, etc. Alright, now the last part here is interval for a mean of a normal population assuming variance is unknown. Now the only difference here is from the last example is the variance is unknown. And now dramatically things change quite a lot. So again, this is the formula or this is the starting point that let x1, x2 up to xn be a sample from a normal population having mean mu and variance sigma square, where sigma square is assumed to be unknown. Now recall that x bar and s square are what? So x bar and s square is the sample mean and variance of a normal population with mean mu. Then now the moment sigma square is unknown, you cannot have sigma square in the interval formula. So we have to make use of a t distribution here. And if you remember from last session, this is exactly how you derive a t distribution. So x bar minus mu divided by s by root n has a t distribution with n minus 1 degrees of freedom. Okay. And similar to how we sort of wrote down a critical value for z, I can actually write down a critical value of t also. So t alpha comma nu. So in this case, nu is what? So nu is nothing but the corresponding degrees of freedom for a t distribution. So now the more important or the only difference between this idea and the earlier problem is that the underlying distribution is no longer z, but it changes to t there. Alright, so I think there is no point of sort of talking about t densities. We talked about in the last session as well that how, so depending on the degrees of freedom, how the t density curve sort of change. Okay. But now more importantly, what is the final interval now? So now things shift from z alpha by 2 to a t distribution. So t alpha by 2 comma n minus 1 there. Okay. So if x1, x2 up to xn are the observed values of a random sample of size n from normal population with unknown mean mu and unknown variance sigma square. So the unknown part is sort of important. Then, so again we have the standardized quantity in the middle, and I can sort of have t critical values as a lower bound and upper bound, and this entire probability now happens to be 1 minus alpha. Thus, the final interval becomes what? So x bar plus and minus a t critical value into s by root n. This would be 100 into 1 minus alpha percent Ci for mean mu. Now, the final point you may wonder is that how do you get hold of this number? So again, you have access to t tables. So similarly, how you have access to z tables, you have access to t tables as well. So if you fix n and if you fix alpha, I can sort of find out the t critical value, and s would be sort of known from the data. So s is the sample standard deviation of the data itself. Okay. So now nothing in this formula is unknown sort of. So since sigma square is unknown, we cannot have sigma here in this place. So we replicate sigma by s, but the important property is that the moment you replicate or change sigma by s, the underlying distribution becomes t there. Okay. Alright, so now in the next session we will sort of explore a bit more on this front, we will take up some examples, and then we will sort of transition into a more important idea called as hypothesis testing. So there we will sort of delve deeper into a z test, a t test, a chi-square test, etc. Okay. Thank you.